Hello everyone, in this video we're going to be talking about the area between curves. Area between curves. And this will be a relatively short lesson because the area between curves isn't really a huge concept. I mean, it's a big concept, but it is not really that hard to understand. So let's have a couple of axes, okay? And I draw two functions. Let's call this f, and let's call this one g. So we have f and we have g. And we have ourselves two regions. We have this region and this region. Now, the first thing you need to consider while doing this is the points of intersection. So let's label these points of intersection. Let's call this one x1, y1. This point is x2, y2. And this third point is x3, y3. It will intersect somewhere down below, but we're only concerned about these two regions. Okay? So how would you find the area of these regions? Okay, let's shade them in a little more. So how would you find the area between these two regions? Now, in order to do this, we have to think back about how we originally found area of a region under the curve. Okay? So at the very beginning, if we want to find the area of this region, we used rectangles. Use rectangles to approximate it, okay? So like this rectangle, this rectangle, this rectangle, and so on. You would keep on adding rectangles. Okay, you're just keeping on adding rectangles. Now, for an area between two curves, you can use a similar concept. So let's zoom into this section, okay? So what we're going to do is we're going to take this section of the graph. Okay, let's copy this. And now so here is our graphs. Part of the blue region still shows, but we're only concerned with the red region for now. Now, let's look at this red region. So I gave you a little hint about how we can represent the area of this red region. Rectangles. Rectangles will be prevalent whenever you're finding area or some other quantity. Okay? And you can draw a rectangle. Okay? So I'm going to draw the graph. Let's not make it purple, let's make it black. And draw the graph. And what you can do is draw rectangles like this. Okay, so you can draw rectangles that span the distance between the two graphs at a particular point. So look how we're drawing all these rectangles. And as you draw more and more rectangles, okay, so we have all these rectangles, okay? And similar to what we did for area under the curve, as we draw more and more rectangles, the approximation for area becomes more and more accurate. Okay, so let's call this delta x. As delta x, the width of this rectangle, this delta x, so as delta x approaches 0, we have a dx, a very, very small amount. Okay, an infinitely small amount. So as you have infinitely thin rectangles and you add an seemingly infinite amount of them, then the area starts to become exact. However, what's different about this is the height of the rectangles. The height of the rectangles. So what would be the height? Well, if this was, redefine this as f, this curve is f, and this curve is g. So g is our bottom function, and f is our top function. Well, that'll just be the vertical distance from this point to this point. So if this is x, then this is g. This is g of x. And right over here is f of x. So at a particular x value, the height of our rectangle will be f of x minus g of x. Okay? So the total area of one rectangle is f of x minus g of x dx. Okay? And remember how we established the definite integral as a sum of these infinitely small rectangles? Well, you can apply the same concept here and take a definite integral. So if this was a and this was b, we would take it from a to b. And that is the area of a region between two curves. The integral from a to b of this distance, f of x minus g of x, times this infinitely small length dx. Okay? So you have this infinitely small length dx times the distance between the two curves. Now, this does not, you have to be very careful about using this formula, okay? Because if I were to extend this, so we recreate that blue region. Okay, so the graph looks like this. Now let's look at this region. Now f is now on the bottom. That's called, now we're going to take the area to C. And C is where the points intersect. Okay? So we always take it from the first point of intersection to the second point of intersection. So this x1, A should be x1, and B should be x2, and C should be x3. Now what about this other region, this blank region? What's the area of that? Now it is not necessarily f of x minus g of x, okay? Because f is on the bottom. So if we do f of x minus g of x, you'll end up with a negative, okay? And we'll have a negative area, which does not make sense. Because area is a measured quantity, and we can't measure negative numbers when dealing with quantities like area or length. So what we have to do is do the same integral, but for g of x, since g is now on top, minus f of x dx. Okay, from x2, our second point of intersection over here, to x3, our third point of intersection over here. And we can generalize this integral as, we can use f of x minus g of x, but if we define these two functions as f of x is greater than g of x. Okay, and that basically means that f of x is our top function. That's what this means. Now we have generalized it, okay? And for any two functions, you can put one function as f of x and another as g of x if you know which one's our top function and which one's our bottom function. Let's do an example, okay? So let's say we had the function, okay? Say we had the function sine of x and cosine of x. And let's say we want to find the area of this blue region. What is the area of this blue region? So this is called as, so this is cosine of x. F of x equals cosine of x, and we have g of x equals sine of x. Okay, so which one is on top? First, what you need to do is find our point of intersection. So where does f sine of x equal cosine of x? Okay, and we need to find the first 2 points of intersection. Well, sine of x equals cosine of x when x equals pi over 4. Because then they both equal root 2 over 2. The same thing, okay, the same thing goes for 5 pi over 4. Because now they're both negative, negative root 2 over 2. Okay, so at x equals pi over 4 and x equals 5 pi over 4, they both intersect each other. Which means that we can take the integral from pi over 4 to 5 pi over 4. Now, which one's our top function? Well, it's pretty clear that our top function, the one I'm labeling in red, our top function is sine of x. So our top function is g of x equals sine of x. So we do sine of x minus, well, our bottom function, the one I'm labeling down here, you can see graphically it's cosine of x. Okay, and they usually do give you a graph on the AP exam. So you can graphically tell which one's top and which one's bottom. So you have cosine of x, sine of x minus cosine of x, dx. And now all we need to do is evaluate this integral. Okay, and if we evaluate this integral, well, what do we get? We get negative cosine of x minus sine of x from 5 pi over 4 to pi over 4. So it looks like we have a problem, but let's substitute in to see if we really do have a problem. So cosine of x and sine of x, so cosine pi over 4, so negative root 2 over 2 minus negative root 2 over 2 minus, we use the fundamental theorem, minus root 2 over 2 minus root 2 over 2. So you have a lot of negatives. We have a lot of negatives. So we're going to try to simplify this to get our answer. So this is root 2 over 2 plus root 2 over 2 minus, so we can distribute this negative sign and turn it into a plus root 2 over 2 plus root 2 over 2. Okay, we have a double negative. And that gets us 2 root 2. So it turns out the area of this blue region is exactly 2 root 2. Okay, looks like we got it. Now, there's some integrals that you can't really do well do a great job of evaluating. Okay? So let's say we had the black axes. Now, let's say we had the function cosine of x. So call this 1. So it's not the neatest drawing, but okay. So this is cosine of x, and right over here, we have the graph. So we have the graph of x squared. So we have f of x equals x squared, and g of x equals cosine of x. Now, what I want to ask you, what's the area of this red region? Now, here is ultimately where we run into problems. Okay? Because the integral is easy to do, but it turns out you cannot take an exact area. Why? Because what's our very first step? Our very first step is to find these two, I'm going to label them in green, these 2 points of intersection. So we know our limits of integration. So if we do x squared equals cosine of x, you start to see a major problem. Okay, because you can't really solve this equation. You can't really solve this equation by hand. Or in other words, you can't really get an exact solution. So what you have to do is take a calculator. So this would be a prime choice for an AP type calculator section question, okay? Because you need to use a calculator to find the solution to x squared equals cosine of x. So let's do our solve feature. Okay, I'm using an 89. You press F2, and then 1, and select solve. So x squared equals cosine x, and we're going to solve that for x. Let's run this. Okay, so the calculator is running. Okay, and by the time we finish this, by the time the calculator finishes, we're going to get a solution. Okay, so we do get a solution. Okay, and as we expected, it's kind of like a symmetrical-ish solution, such that we have x equals plus and or minus 0.8241. Okay, so these are the 2 points of intersection, and we don't need to worry about the y coordinates. We only care about the x coordinates. So what we can do now is take the definite integral from negative 0.8241 to positive 0.8241 of, now what's our top function? The top function is cosine of x, see? It's our top function in orange. So that's cosine of x. So our top function is cosine of x minus our bottom function. Our bottom function noted by blue is x squared. So the integral itself is not that hard to evaluate, okay? But it's because of these points of intersection that you're going to need a calculator for this part. So you integrate the function on your calculator. Okay, so you have cosine x minus x squared. We integrated with respect to x from negative 0.8241 to positive 0.8241. Okay, and we get a final area. We get a final area of 1.0948. 1.0948. Okay? What you also could have done is take the integral from 0 to 0.8241 and multiply it twice, since it's symmetric with respect to the y-axis. Okay? So the y-axis divides the area perfectly in half. So you can just have taken the integral from 0 to 0.8241 and then multiplied that area by 2. And you would have gotten the exact same answer. So whichever method is easiest for you, that is the method you should use. But remember, you should always subtract the bottom function from the top function, okay, so that you get a positive answer and you keep your answers positive, okay? So this topic is quite particularly important, okay, particularly important in that it's usually asked a lot on the AP exam, okay? In next video, we're going to talk about another very important topic, and it's also geometric as well. Okay, it requires some visualization, but it can be done. Okay, and we'll see next video that the integral is a lot more powerful than you might think. Thanks for watching. Please be sure to comment and like this if you have any questions, and like this video. Thank you.